mean, A and B were doing just fine being in a bond all by themselves. Hello, welcome to this overview of radical reactions. We don't learn very many radical reactions in this course, but they are significantly different than the typical traditional reactions that we do learn in this course. Our main truth of organic chemistry, that negatives attack positives, doesn't actually apply in radical reactions. Before, all of the reactions that we have seen, and most of the reactions in this course, are what we call heterolytic bond cleavage. And what that means is that when a bond breaks, those electrons are distributed unequally. Both atoms in that former bond don't necessarily share those former electrons the same. Heterolytic, breaking differently, so we are breaking the bonds and distributing those electrons differently. If we look at an example like an acid-base reaction, we'll just do a generic acid-base reaction where we have some generic base, B lone pair with a negative charge, and some generic acid, HA. Our traditional arrows for this mechanism would be the base attacking the hydrogen, building up too much electron density around hydrogen, so we break the bond and push those electrons onto whatever A is, and we form a new bond between the base and hydrogen, and we form a new conjugate base, A lone pair with a negative charge. Each of these arrows represent the movement of two electrons. And when this former bond breaks, both of the electrons go to whatever A is. So A gets both electrons, and the hydrogen that used to be part of this bond gets 0 electrons. Both of the electrons in that former HA bond go on to whatever A is. This is different in homolytic bond cleavage. Homolytic bond cleavage says that when a bond breaks, the electrons are distributed equally between the two atoms in that former bond. So if we look at a bond between two generic atoms, A and B, when we break this bond with homolytic bond cleavage, we're going to break this bond and we're going to push one electron from that bond onto each of the two atoms. And we're going to form two radicals, radical A and radical B. Notice what's different here. We have what's called a single barbed arrow. Where a traditional arrow shows the movement of 2 electrons, a single barbed arrow shows the movement of 1 electron. This bond between A and B had 2 electrons in it. When this bond broke, we took one of those 2 electrons and moved them onto A as a new radical, and one of those 2 electrons onto B as a new radical. The electrons were distributed equally between A and B. This is different from heterolytic bond cleavage, where both of the electrons went with one of the atoms. Here, 1 electron each goes with each of the atoms. The electrons are distributed equally. So some overviews here with homolysis, the homolytic bond cleavage. This is not a favorable process. I mean, A and B were doing just fine being in a bond all by themselves. We didn't need to break them into their radicals. In fact, that's why bonds form, because bonds are more stable than 2 individual atoms unbonded. So in order to do this process, this is an uphill, unfavorable process. We need to input energy into this system in order for this to happen. And when we input energy into the system, there's a couple of ways we can do this. One of the ways is to add heat. Another of the ways is to add light. What we need to do is add energy. We can either add thermal energy in the form of heat or electromagnetic energy in the form of high energy photons or light. Another thing that's true about homolysis is that it rarely happens. Again, the bond was doing just fine being a bond. It didn't really want to split into 2 atoms. And so even when we input a lot of energy into the system, this still doesn't really happen very often. It's a high activation energy barrier, and it's not a favorable process. And so the concentration of radical at any given time in a system is often very low. There's not a high concentration of radicals in the system due to homolytic bond cleavage. The third thing that we want to know is that this often targets the weakest bonds. If this is a not favorable process that doesn't happen very often, the strongest bonds are going to be resistant to this process, and it's just the weakest bonds that are going to break in this process. And so the weakest bonds in most systems tend to be bonds between 2 heteroatoms. A Z-Z bond. This tends not to target carbon-hydrogen bonds or carbon-carbon bonds. Those bonds tend not to undergo homolytic bond cleavage. Tends to be the weakest bonds. In fact, this is a good thing to look out for to know that maybe we're doing some kind of radical process. If I see a bond between 2 heteroatoms, that's fairly rare. Typically we see a heteroatom bonded to a carbon. But if we see, say, a bromine-bromine bond or an oxygen-oxygen bond, those types of bonds tend to be very weak. And so those are the ones that we can target through a homolytic bond cleavage reaction. Now, if we look at radicals, radicals are similar to carbocations. We don't see them very often, so let's remind ourselves some things about radicals. They're similar to carbocations, which means they're sp2 hybridized. And because they're sp2 hybridized, because they're similar to carbocations, we can classify them the same way we classify carbocations. A radical can be a methyl radical or a secondary or a primary or a tertiary radical. And the stability trend is the same. Tertiary radicals are more stable than secondary. There are a couple of exceptions, differences between radicals and carbocations. Carbocations are cationic. Radicals are electronically neutral. They don't have a formal charge. They are electronically neutral. And the one big difference that we need to keep in mind with radicals different from carbocations is that radicals do not undergo rearrangement. Okay, so these are some things to know about radicals. Let's talk about how radicals are used in reaction. There are only 3 elementary steps that we can do with a radical. All radical reactions will be composed of one of these 3 elementary steps. We can mix and match them, we can use them in different orders, we can use them multiple times, but it's only going to be really these 3 elementary steps in radical reactions. And one of those elementary steps is what we call atom abstraction. And what that means is that if we have a radical, get it, a radical, these are the jokes, people, and we react that with some molecule, some bond between 2 random atoms B and C, we can abstract one of the atoms from this bond. This radical can abstract one of the atoms from this bond. What that means is it wants to form a new bond between, let's say, A and B. So if we want to form a bond between A and B, we need 2 electrons for that bond. Where can we get those 2 electrons from? We can get one of those electrons from the radical. We'll use one of those electrons to form the new bond with atom B. The other electron is going to come from part of this bond between B and C. So we'll take 1 electron from A, 1 electron from the BC bond, and that will form a new bond between A and B. Now, when we break a bond like this, we must account for all of the electrons. There's still 1 electron unaccounted for. That electron will move on to atom C as a new radical. So we'll form a new bond between A and B, and we'll form a new radical on atom C, whatever atom C happens to be. So this is atom abstraction. Another possible elementary step that we can see with radicals is alkene addition. And in alkene addition, when we take a radical and we want to react it with an alkene. Now, this notation here, I'm not suggesting necessarily that these are methyl groups, just that I recognize that carbon makes 4 bonds, and so I'm including enough little tick marks to show that, yes, I understand carbon makes 4 bonds, but what I'm really focusing on is the alkene in this system. Alkene addition, I want to add this radical to the alkene. I want to form a new bond between the radical and one of the carbon. That bond needs 2 electrons. Where can we get those 2 electrons from? I can get 1 electron from the radical, and I can get 1 electron from half of the pi bond. Take 1 electron from the pi bond, 1 electron from the radical to form a new bond between the radical and carbon. Again, I need to account for all of the electrons though, so there's still 1 electron unaccounted for, and it will go on to the carbon. So I'll form a new bond between the radical and the carbon. I'll break the pi bond. This carbon will now have a radical, and the carbons still have enough bonds to make 4 bonds. But we have a new radical on this carbon because we've broken the pi bond and pushed 1 electron onto that carbon. Again, we're using our single barbed arrows, these fishhook arrows, to show the movement of 1 electron. And the final possible elementary step for a radical reaction is combination, also sometimes called coupling. And that's when we have 2 individual radicals, and we want to form a bond between 2 individual radicals. We're going to need 2 electrons for that bond. Where can we get those 2 electrons from? We can get 1 electron from radical A and 1 electron from radical B. Those 2 electrons will allow us to form a new bond between atom A and atom B. Now, the thing about combination steps is that these are relatively rare. Remember, the concentration of any radical at any given time is low because the homolytic bond cleavage is an unfavorable process. So it's rare to even form 2 radicals. For 2 radicals then to swim around and find each other in solution is going to be even more rare. And then for them to combine in a coupling reaction, this is a fairly rare occurrence, but it can happen. Okay, this is a good overview of radical reactions. In a subsequent video, we will start to learn some of the radical reactions, but this gives us an overview of what we're about to see.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.